All right, we're going to turn the time over to Ben Moulton, and he's going to get into some mechanism design for the morphing things. And this is our last, so we've got about 30 minutes. Ben's going to go over this till 11:30, and then we're going to break for lunch. And I know we've been kind of plowing through things, but just hold on for another 30 minutes. We'll take a break here. So.
Okay. My presentation is going to be a little bit of a change of pace. 1 second.
Do you want me to pull up these slides?
Yeah, if you would, thanks. I'm just getting my toys ready. About these in a minute. Okay. Thanks. Okay, so we're going to be talking about 3D printed morphing wings. Like we've, I'll go over a few of the definitions that we've made so far, just so they're a little bit fresher in our brains. So I'll skip past this part. So once again, the whole point of what we're doing is we're trying to get rid of the vertical stabilizer. So it's a little bit of a general, it's a very general statement, but we can more or less control roll and pitch just with the main wing, with our ailerons, with our elevators. But yacht's a little bit harder to control, and Zach will get into the methodology of how we'll do that a little bit later. But I wanted to talk about how we make this morphing mechanism that we will use to control yaw on this flying wing aircraft. So the manufacturing methodology that we ended up sitting on is fused deposition modeling, FDM, commonly known as 3D printing. So there's several benefits to 3D printing. So the first is repeatable. That means that I could take an STL file, put it in a slicer. So what we have pictured here is just a SolidWorks rendering, but there's a CAD, or excuse me, a program that you then take this solid object file, you stick it in there, and basically it discretizes this object into layers so that the FDM printer can create it. And so I can take this part, stick it in the printer, and I'm able to get the exact same part if I take that same file, put it back in the printer and print it out again. It's also replicable. So that means that I can take these same part files, these same printer settings, hand them to someone else, and they'd be able to print the same object. It's also very quick. So, and we especially noticed this in the design process of the morphing mechanism. We'd be working on, design 3 while we're printing design 2, while we're playing with design 1. It was a very nice process to be able to rapidly create these objects that we could prototype and test and play with. Another benefit to 3D printing, it's very cheap relatively to other manufacturing materials. PLA runs $20–30 a kilogram, and so it's not expensive stuff. You're able to create these small prototypes and play with them, and they're pretty cost effective. And the last thing that I wanted to hit on is that they're pretty durable. I mean, we'll get into the actual durability of an aircraft created from 3D printing materials a little bit later when we talk about flight testing, but for all intents and purposes, with a little bit of a spar or something like that, it works great as a wing structure. And so now that we've addressed the manufacturing method, I wanted to talk a little bit about the motivation for why we wanted conformal flaps. And Dr. Hunsaker and I believe Zach have hit on this a little bit earlier. But there's 2 bigger reasons why we care about having a parabolic flap. So over here on the left are pictured 2 different airfoils deflected. One is, they're both a NACA 2412. One is deflected using an articulated flap, so that means a straight rotation about the hinge point. And the second one is a conformal flap, what we're also calling a parabolic flap. So these 2 control surfaces are deflected to the same deflection amount. But something that I want to point out here is on the top in this dashed dot line, we have the camber line slope, or excuse me, the camber slope of the NACA 2412 airfoil. And then the dashed line right here that is the camber slope of the articulated flap. So you'll notice this discontinuity right here. And so what that does is it causes flow separation. And that's something we want to avoid. And so if you'll notice, the parabolic flap camber slope is first order continuous. So it doesn't have that, that flow separation that the articulated flap does. On the right is the second reason, or a second reason for preferring the parabolic flap. And this shows the increased flap effectiveness, or excuse me, the ideal flap effectiveness. So the ideal flap effectiveness is basically if you had an airfoil that were deflected by some flat chord fraction. So this is flat chord fraction on the x-axis. So as you can imagine, as we go all the way out to a flat chord fraction of 1, this airfoil slowly becomes the whole thing is a flat. That just means that 1 degree rotation and angle of attack is the exact same thing as 1 degree deflection. And so with the articulated flap, you're able to approach a value of 1 of effectiveness. But with the parabolic flap, because it's more efficient, it's able to approach higher values. So we end up hitting an ideal flap effectiveness of 1, somewhere around a flat chord fraction of 0.4. And so that's the second reason why we stuck with the parabolic flap. And so now that we've talked a little bit about, the motivation for why we care about morphing wings and how we're going to do it, I wanted to talk a little bit about the criteria that we decided on for this morphing mechanism. So the first one was based on some preliminary evaluations. We were able to determine that we needed to produce plus or minus 20 degrees deflection. So that's, I guess I should define that we call positive deflection, downward deflection of the flap, and negative deflection, upward deflection of the flap. The second thing that we needed it to be able to last at least a flight. We weren't terribly concerned about the aircraft surviving more than 1 flight. And so we wanted it to last at least 1 flight. We were a little bit optimistic. We decided, let's call it a 10-minute flight. And let's say the control surfaces are moving up and down about once every second. So that's about 600 cycles. We need our control surface to be able to at least withstand that many cycles. The third limit that we needed was more of a structure-based limit. So most general aviation aircraft have load limits somewhere in the 3 to 6 range. Fighter aircraft have higher load limits. And so based on a couple FAA rules, we decided that 4 Gs was a good limit. And once again, when we get to flight testing, we'll talk about whether that was a good limit or not, or a good goal. And the last thing, and this will make a little bit more sense later on, was the difference between our actual conformal flap and the predicted parabolic flap. And so what we wanted there to be about a 10%, at least at minimum, or excuse me, at maximum, a 10% difference in percent chord between our parabolic flap and our actual mechanism. And once again, that I'll have some figures later on that'll make that a little bit clearer. So now I want to talk about a couple of the designs that we talked about, or that we came upon. As was mentioned earlier, we conceptualized 18 different designs. We ended up really with 2 designs that are worth talking about. Several prototypes. So this first one, I'm only going to go on it briefly because we some later analysis, and I'll talk about the later analysis in a minute. Some later analysis found that we actually wanted to have a different airfoil, compliant airfoil design. So this first one is called the ARCS mechanism, and I won't go into too much detail on that. But once again, this has camber line conformity. It's a simple design, and so just to clarify on this picture in black, you can see what would be printed in PLA. So that's typically hollow in the leading edge, and we'll be able to look at a couple pieces later on. And then in blue is what would be printed in PLA once again, but not hollow. That would be 100%. So PLA, polylactic acid, is kind of a stiffer material. And then the green is TPU, so thermoplastic polyurethane, and that's more of a stretchy material. That's like what your phone case would be made out of. not quite silicone-y, but a very similar feel. And so this device would be internally actuated. So there's a servo sitting somewhere in the leading edge up here, and it pushes and pulls on this tongue, and it's able to deflect this airfoil. Something that I'll stress later on, but I wanted to bring up right now. The purpose of at least my part of this research was not to determine the best morphing mechanism ever. It was to find one that worked. And so there's plenty of things wrong with our design, with our system. But we found one that worked, and that's the biggest reasoning behind a lot of the design choices that we made. And so I wanted to talk about the second design that we came up with. Similar concept that has an airfoil, or excuse me, a servo motor sitting inside the leading edge that pushes and pulls on this tongue. The main difference between this design and the previous design is that this one is 3D printed fully from a single material. So it's got these spring-like objects in the trailing edge. So those are done to conform the thickness distribution, so it stays the same along the surface of the airfoil when it is deflected. So we need to do one more definition, and then we can talk a little bit about the testing that was involved with these mechanisms. As was mentioned before, I believe Dr. Hunsaker brought this up. We looked at two different control surfaces designs. The one on the left is the continuous control surface, so that image shows it pretty well. I think it shows that the trailing edge is linearly interpolated between these control ribs. And once again, that as you can probably imagine, that would probably be more in line with the ARCS concept. That was the stretchier concept. So we'd have these different control surface, or excuse me, these different control ribs, and they would be pushing and pulling on this trailing edge. And the second one was the discrete control surfaces. So the wing was discretized into sections, and rather than having a linear change in the trailing edge, they were purely deflected up and down, treated more like flaps rather than this stretcher material, and that was more in line with the kinks mechanism. And so now that we've got that a little bit clearer, so I wanted to get into a little bit of the testing that we did with our mechanisms. So the first test was an airfoil test. So basically it means we printed out a 2D section of this airfoil, and then I would print out a piece of paper with the actual parabolic shapes that same airfoil, and I would compare it. I would take videos, and we would make sure that, can we get plus or minus 20 degrees? Can we have this same parabolicity effect? Are we able to approximate this parabolic shape? And so that was the biggest reasoning for that type of testing. And so, and once again, this was an iterative process. It didn't always, it would fail the airfoil test, we'd go back, we'd do it again. So after we did some airfoil testing, we'd move on to testing the actual wing. So the main point here was to examine geometry effects of sweep taper dihedral, looking at how two opposing actuators would work on a control surface. And this was more in line with the continuous control surface that we talked about a little bit earlier. So for example, on this one right here, you can see a little bit of buckling on the upper surface of this wing. And so that was one of the things that we realized, we're going to have to change this design. That was a concern for deflecting these wings. So after that, we were able to stick in servo motors and see how we were able to control this mechanism. And so some of the things that we would solve here was, where do we put the servo? How do we orient the servo? Where do we attach it? Do we attach it to the trailing edge? Do we attach it to a tongue? So many problems that you have to solve. And another big concern here was, can a servo motor control it so that we can deflect, this plus or minus 20 degrees? So like, for example, in this video right here, you can see this middle control rod buckles pretty bad. And so that was a concern, how do we work with, do we stiffen the control rods? Do we decrease the stiffness of this mechanism? How do we mess with that? And so the final step in this testing process was to use a poor man's wind tunnel. So I'd stick these wings out of a car window, and we'd drive around right about the flight speeds that we would expect on the Horizon aircraft, and we'd see, you know, do the servos still work with air going over the wing? How does the structure hold up? And we'll talk about that one a little bit later. One of the bigger concerns before we got into the 3D printing was looking at, and I'm hesitant to call it flutter because we're not talking about air elastic flutter, but we get this fluttering of the trailing edge on these lighter foam concepts that we didn't notice as much with the 3D printed mechanisms. But all these problems that we were able to solve with all these different testing. And so, as you can see, as we step through this design process, we were able to come up with these two solutions, the arcs and the kinks, and we were able to meet some of these constraints. Or I should say, we met all of them with one of them. Once again, you know, we weren't trying to create the best morphing wing mechanism. We were just trying to find one that worked. So right here are some lessons that we learned along the way. These are lessons that you may or may not learn if you take the same process. These were just things that helped us along the way. So one thing on the right, you can see pictured one of these bi-material prints. So this one's the white is PLA, the black is TPU. So the white is that stiff material, the black is the stretchy. One thing we learned was that the closer the print temperatures were between the two, the better they meshed together. So for example, the stiffer material prints at about 200, 220 degrees Celsius, and the stretchy material prints at about 230, 240, 250. So you can have anywhere between a 20 to 50 degree difference in Celsius. So for perspective, for a lot of us that work in Fahrenheit, that's the difference between freezing and a hot day like 90 degrees. It's a big difference. And so these materials didn't mesh very well sometimes, and so we had to narrow down that temperature difference. Another thing we learned, and that was thanks to some collaboration with SDL, we were able to find that we wanted to print lighter colors. So certain materials will absorb heat a lot better when they're sitting out in the sun, and we tested a couple of those types of things. And so we wanted, you know, that's why Horizon is white now. So a final lesson, and this one is definitely design dependent, was we learned we wanted to stick to a skin thickness of about 0.8 millimeters. And once again, that really is dependent on the design and on the manufacturing method involved. So we have all these things that you guys are welcome to play with. I'm sorry for the people online who can't play with them, but I have a smattering of some of the designs that we've looked at, some of the changes that we made, some of the more influential changes. And so pictured there, you can see a whole bunch of the designs. This was, oh golly, this was a while ago. I think that if I had to guess, that's probably about the first half of the designs that we've tested. But once again, just iteration after iteration, I think the biggest way to sum up my research was that we were moving fast and breaking stuff. We just wanted to get go and find one that worked. And so here are a few pictures of some more mechanisms. And once again, I could go into more detail, but we're running a little bit out of time. But this is it goes from top left to right as you go down. That's kind of the progression that we went through. We started off with these 3D printed designs. We started adding this flexible material, and then some studies that we found later on showed that we really didn't need to. It would actually produce better results to control yaw if we had discrete control surfaces, and so we leaned more towards a design that would be optimal in that situation. So here are the two morphing mechanisms, the two morphing airfoils, deflected plus and minus 15 degrees. So on the top we have that arcs design, and on the bottom we have the kinks design. And I won't belabor this part too much. So you can see a little bit what the deflection looks like on these two. So you can see the stretching of the trailing edge on the ARC's continuous control surface design. And you can see the way the control surfaces kind of slide span wise a little bit on the Kink's discrete control surfaces design. So hopefully it was obvious. If it wasn't, oh well. We ended up going with the Kink's design. Once again, that's because of the desire for these discrete control surfaces to better control yaw. Shown in a blue box is an approximate position for the servo. It wouldn't be cutting into that spar, but it would be located somewhere in the leading edge so that it would have the servo arm sticking down, and it would be able to push and pull on that tongue right there. And on the bottom is a CAD rendering of the final Horizon aircraft. There's a couple things you might notice about that we'll get into detail a little bit later. But yes, we ended up with the Kink's design. We actually ended up moving the Kink a little bit aft and shifting it inside of itself. And that was done to improve the parabolicity of the deflected control surface. So here's a picture of the final design deflected. This is an older design, but here are some of the servo deflection values. So once again, we were going for plus and minus 20 degrees, and we're easily able to meet that. Normally we're getting about 25, 30 degrees, and most of the time that's limited by the servo. That's not a mechanism limitation. And so those are, forgive the notation, but in that plot on the right. So those are the center section on the far right and moving out span wise as we go to the wingtip on the left. And so those are decreasing average chord lengths of those sections, and then the up and down deflection of those control surfaces.
So each segment has 3 actuators, so total 9.
No, so each segment has 1 actuator, and then there's 5 wing segments and 1 center section segment. So there's 11 control surfaces and 1 servo for each. So the second thing we looked at was fatigue testing. We did a deflection range of plus and minus 25 degrees. And then we used the two different servos that we were using on this control surface, or excuse me, on this aircraft. And then we just had it deflect back and forth and see how long it took for the mechanism to break. So the first design was a larger servo. We went for about 15,000 cycles. Once again, it was about 600 for a flight. At max, at the most, it would be 600 cycles per flight. And so after that long enough, we decided, you know what, it's going to be fine. And then, we tested the smaller servo up to breakage. That's probably not a real word, but oh well. And we tested it up until the servo broke, and the mechanism was just fine. And so we passed that requirement. The second to last thing was load testing, making sure that this structure would be able to take the 4 Gs required of it. So we ended up loading up a section of Horizon with a force of 153 pounds. And there's the bending moment that we calculated on that, which created a load limit of about 4.88 Gs. And once again, we'll talk a little bit later about how that was a little bit underestimated on this aircraft. Okay, so the last thing that I wanted to address was this parabolicity study. So what we did was we took a picture of the airfoil deflected to some known amount, and then we took the analytic prediction for the outer mold line of this airfoil deflected parabolically, and we compared the two. How far off does the average point along this outer mold line compare to the outer mold line of the predicted estimate? And as you can see with the Kink's mechanism, we were able to get less than 10% difference there. Okay, so in conclusion, the ARC's design is able to deflect 2.5 degrees per inch in the stretchy trailing edge gradient, and the kinks control surfaces can deflect at least plus or minus 20 degrees. And this is a little clip of a video we'll talk about later on. So this is my favorite, about 5 seconds of flight testing footage that we have. So this is just a review slide. Once again, it met that requirement of a plus or minus 20 degrees. We met that fatigue limit of about 15 of the 600 cycles well over. We met the load limit that we predicted, and we met the parabolicity, excuse me, difference that we predicted. For more information, you can see this conference paper. Thank you for attending, and I look forward to answering your questions.
All right, well, we got some structures gurus in the room, James and Greg, Rich. I know Greg's done a lot of 3D printing stuff as well. Any questions from you guys?
So, for example, this one. So without any external load, you can keep this kind of shapes, but under the load, it can be thinner like that. So doesn't that affect your estimation or anything?
It does, and that is something we didn't look into. But yeah, that's a good point.
But our final design shouldn't have that. I mean, it will still have some of that, but the skin is a lot stiffer on our final design because it's all.
This is the final design. You can see the spar shape.
Still, it is.
Yeah, yeah.
And actually, we noticed that would generally happen a lot worse on smaller span-wise sections. When they were larger, it was, and there were several factors, but that's a good point.
You can go back to the flight test video that you had there, though. I mean, those are some pretty big deflections, and you can see how a little bit.
They do have a little bit of, well, I think one of the worst things I think about the mechanism is it has a little bit of slop and twist or a span-wise twist, if that makes sense. I guess it's not really twist, but you can see it a little bit here that the root section and the tip of each section kind of do this wobble effect. And I feel like that's, if I were to go back and change it, I think one of the better ways to fix that would be to stick 2 servos in each section, but that would increase the weight quite a bit.
And also the side was not closed, and doesn't that?
You get
affect?
spillage.
Oh, yeah. Yeah.
So were you able to see some effect because of that? Or-
Well, we haven't measured much from the flight test. Most of our flight testing experience has simply been getting this to work. So unfortunately, we don't have data, to tell us if that, like how far off our estimates are from flight test data. So, and we could have done this in the wind tunnel, but again, bandwidth and time, we just.
Need a sunroof and Ben can hold it up the top of the car.
Yeah.
The whole thing.
10 miles per hour.
So I have a question, Ben. Is there, I mean, it relates to what James just said. I noticed that you have there's a time difference between each of the flaps deflecting enough that would you be able to coordinate those so that there's less spillage? Does that make sense? Are they supposed to be deflecting all the same amount in this video, or are you flying in mode?
Flying in mode 1, so yes.
So yes. So that was my thought, was if you could somehow get them, tune that a little better so that they're not quite so different as far as the deflection time.
Yeah.
Yeah, I don't know. Is that something that you've noticed has an effect on it?
So and we'll be able to look at it in a minute, but so because it's only got one single fixed point that it's pushing on, it's the weirdest thing, but sweep and taper seem to have opposing effects on this control surface. So sweep makes it want to push I believe, inboard, but taper what makes it want to push outboard, and that may be flip.
Okay.
But they fight each other, and it's the weirdest thing, but I believe it's the middle section, it seems to have the least amount of sliding of that bottom of the tongue,
Gotcha.
and so.
It gets there faster, so to speak, yeah.
And so, and part of the difference, you know, there's several reasons. One of them is this twisting, you know, of this trailing edge. Another reason is we have these slots cut in between, there are these triangle cuts, and it might be easier to see. Where did I have it? Right there, but that was just to prevent the control surface from binding when they went up and down.
Yep.
And so that's part of the reason why you can see these bigger differences is because there are gaps. But once again, I think the best way to solve that problem, if that were to be the next step, would be to either have I'd have to think about it for a while, but the first thing I can think of is to have two servo motors, two connections, so that it's not just pushing on one point, it's pushing and pulling in line with the flow.
The other thing, that video kind of exaggerates the gaps that you're saying.
Sure.
Because the camera's sitting right there, looking at, do you know what I mean? So when we plot the aircraft here in a minute, it's not as bad as that video makes it look, but.
So that aileron in the fuselage, is that how you're trying to? create
Yeah.
that bell shape?
Partially, yeah, exactly. So that, we call that the whale tail. But yeah, it's that center section and that thing can deflect, and yeah, that's controlling our
That's what I meant.
lift
So,
at the center.
so center is, if it is more aerodynamic, then we probably can create more lift
Yeah,
from there. But so probably, I don't know, that another discussion will be follow, but this is just a mechanism, but I saw, what is it called? At the tip.
oh, the winglets,
The winglets.
yeah.
So if this meant to be flying without,
Right, without vertical surface, so we have vertical surfaces on there.
so when you take that off, then are you confident that you can fly and control this?
But we're not sure. So the point, so we put vertical surfaces on there because we have to flight test this before, as we're learning about the yaw on this, right? So part of the flight testing, we'll get into the flight testing stuff later in the control algorithm and everything. If it were all working, yes, we should be able to remove the vertical surfaces, and the active yaw controller on board would produce yaw damping and yaw stability and everything actively by using the yaw control. But because not all of our flights have the yaw controller running, we have to have vertical surfaces on there. So yeah, so it's just something we had to do as part of the flight testing here, but the point is exactly to be able to get rid of those. Yeah. Okay.
Yeah, I think it looks like, yeah, so there's a lot of lessons, kind of to try and learn kind of things.
Yeah.
So I can see the pain that we have to go through. So, yeah, great job.